To be viable, a structure must possess four properties: equilibrium, stability, adequate strength, and adequate rigidity. The most basic requirement of any structure is that it should be capable of achieving a state of static equilibrium in response to any load that is applied to it. Buildings are subjected to forces caused by various agencies, one of which is wind, as shown here, which causes pressure forces to act on its surfaces, the accumulated effect of which is here represented by a single horizontal force. Isaac Newton told us that objects to which forces are applied will move unless equal and opposite forces, called reactions, are also present. In the case of buildings, the equal and opposite reactions come from their foundations. This building is now in equilibrium so far as horizontal forces are concerned and will not move sideways. But because the forces are not aligned, it can rotate. To prevent rotation, a downwardly acting vertical reaction is required at one side, and this causes an equal and opposite reaction to occur at the other side. The building is now in a state of static equilibrium and will remain stationary. One of the conditions for equilibrium is that buildings must be connected to the ground by foundations that are capable of generating the reactions that are necessary for equilibrium. This is a design consideration. For equilibrium, two conditions must be satisfied. The forces must balance in all directions, and there must be no turning effect. If these two conditions are not satisfied, the building will move if any forces are applied to it. If labels and dimensions are added to the diagram, these two conditions for equilibrium can be summarized in three equations. So in this diagram, L represents the loading force, R is the horizontal reaction, V1 and V2 are the vertical reactions, H is the width of the building, and V the vertical distance to the point at which the load is applied. For horizontal equilibrium, the two horizontal forces must balance. L equals R, L minus R equals 0. The two vertical forces must also balance. So V1 must be the same as V2. And for rotational equilibrium, the moments caused by these forces must also balance, and this can be tested by examining the turning effect of the forces about a single point in their plane, and the left-hand end of the building has been selected here for that purpose. The forces R and V1 pass through that point and will not have any turning effect. L will cause a clockwise turning effect, and V2 an anti-clockwise turning effect, and these two turning effects must balance exactly. So L1 times V minus V2 times H equals 0. These are the three equations of equilibrium which represent the two conditions for equilibrium. We can put numbers onto some of these arrows. The load at the beginning of an analysis of a structure, which is the process by which the loads and forces acting on and within structures are evaluated, at the beginning of the analysis, all loads to which a structure is likely to be subjected must be predicted and evaluated. The case shown here is due to the horizontal action of wind. The magnitude of the load can be determined from loading standards and is obviously a prediction based on meteorological data. But L should be known at the beginning of the analysis. The dimensions of the building are also known, so the only unknowns in these equations are the three reactions, and these can be calculated from the equations. R can be calculated from the first equation. V2 is the only unknown in the third equation and can be calculated from that. Once V2 is known, V1 can be calculated from the second equation. What is being demonstrated here is a basic principle of structural analysis, which is that a physical property, in this case equilibrium, is used to generate sets of simultaneous equations from which unknown forces can be calculated. Other physical properties, such as elasticity, which determines the way in which structures deform under load, can also be used to generate equations. But equilibrium forms the basis of all structural analysis. Looking at a less abstract example, buildings taken as a whole must be in equilibrium. For example, in response to the weight of everything acting downwards, as indicated here. In order that the building taken as a whole can be in equilibrium, all of the individual parts must independently be in a state of static equilibrium. The reactions required by each element are felt as loads by the elements that support it. So the reactions required by the roof truss here become loads on the walls which support it, and so on down through the building to the foundations. This means that the connections between the elements must be capable of generating appropriate reactions. Application of the equations of equilibrium to each individual part allows all of the forces that occur within the structure to be calculated. Equilibrium is fundamental. Without equilibrium, the structure, and with it the whole building, will collapse when load is applied. Equilibrium is a necessary condition for satisfactory structural performance. It is not, however, a sufficient condition. Stability is the second condition that must be satisfied by a structure, and is the subject of the next presentation in this series. But before that, let's look at a structure that may appear to circumvent the principles of equilibrium. This sculpture by the designer Santiago Calatrava. The blocks that form the piece are not by themselves viable as a structure, and must be tied at their tops with a thin wire, which of course Calatrava would prefer that we did not notice. Even with the wire attached, the structure seems to achieve an impossible equilibrium. The weights of the blocks will act through their centre of gravity, which is located in space below them. This weight can be resisted by a single reaction acting at the base of the lowest block. The system is not in equilibrium, however, due to the rotational effect caused by the misalignment of the two forces. A second reaction is required at the point where the thin wire is connected to the foundation. In order that the three forces can balance vertically, the size of the first reaction must now be increased. The vertical equation of equilibrium can now be written. For rotational equilibrium, the moments of the forces about the base of the lowest block must balance. And that allows a second equation to be written. If the weights of the blocks are known, W will be known, and the magnitudes of the two reactions can be calculated from these two equations of equilibrium. Although the sculpture appears to defy the principle of equilibrium, it must nevertheless comply with the requirements of equilibrium. Note that in order to comply, the magnitude of R1 must be considerably greater than would be required to support the combined weights of the blocks if a simpler arrangement had been adopted, for example, if the blocks had simply been stacked on top of each other. Designers who wish to create spectacular, gravity-defying structures, as in much recent architecture, should realize that it comes at a price, which is the generation of large forces that have to be resisted by strong materials, often in large quantities. The conditions for equilibrium must always be complied with. The consequence of apparently not complying with them should always be carefully assessed.